So hey guys, this is Ayusing, and in this video we are going to talk about the mathematics for the large margin classifier, and I think this would be beneficial for who is interested in to get more intuition behind a large margin classifier, as why large margin has formed and how. So that's why I come up with this video, and I think this video is a little bit important because here I will be teaching you about a vector inner product also. So this would be helpful in your academics and also for your in deep learning or for the machine learning journey. So be sure to take a look at this video and try to understand the topics. So as I will be making the mathematics behind the large margin classifier in the simplest form that I can be. So without wasting time, let's get into it. So first of all, let's talk about the vector inner product. I think I had not tell you about the name, but we have perform this kind of equation, and the vector inner product is nothing but the transpose times the particular vector. What do you mean? Let me finish. Okay, so there is a vector W and V, which is a two-dimensional vector. Both are the two-dimensional vector, and we want to take the vector inner product. So we want W transpose V, and what the solution is, and this is called the vector, because we have a two vector inner product. Okay, and this is called the vector inner product. What we have to do, we have to transpose the W and multiply the vector B. So there are two solutions that I can found. The first solution is I can simply the first solution is the main solution that I'm going to talk about, and the second solution is very easy, which we'll be taking a look at that. So first of all, let's take a look at the first solution. So here, let's plot this W vector onto our this XY and plane. So this is a two-dimensional vector. I can easily plot it. So let's say the vector is an ray here. This is an ray, and this is a vector, W vector. Okay, and let's plot the V vector. The V vector. This is my V vector. Okay, we have plotted just right there. Now, just to give you information that we'll be using this, that how do we take out the length of this vector, means W? How do we take out the length? For taking out the length, we usually denote, you might be seeing this or you might be familiar with this, we have a norm, or taking out the length of the vector. So here is my W vector. Now if you want to take the length of a W, so we usually write that as this, something like this. Okay, and this is called the norm of W, and simply the length of the vector W. Okay, we are just taking the length of the vector W, and you might be thinking, what is the equation for that? For taking out the length, you are going to use Pythagoras theorem. And what does that mean? It's you might be familiar with Pythagoras in class 7, I think so. So don't worry about it. I'm just going to show here. Here we have a two-dimensional vector, so we squared it up. W1 is squared plus W2 is squared, and we are taking the square root. And this is the Pythagoras theorem. Okay, Pythagoras theorem. And here we are just taking the square of each and every element in the vector, and we are just summing them up and then squaring them up. We are taking the square root of them, and we are getting the length of the vector. Okay, I'm not going to deep dive into the kind of the algebra, linear algebra part, because there is also always a Khan Academy, you can take a look at that. But for now, for learning machine learning, I'm going to teach you this. This is something like the norm of W. It simply means the length of the vector W. Okay, and we are just going to take the length of the vector w by w1 squared plus w2 squared. Okay, now we want to take the vector inner product. It simply means w transpose v. So here is the vector w and here is the vector v. So here I will choose the different color, yeah, green. So if I project the vector v, if I project the vector v onto w at a right angle, this concept is called orthogonality. Okay, orthogonality. If I project this vector v at a right angle onto the vector w, and this whole, let me use black, and this whole is the projection of vector v onto w, and we denote it as p. Okay, and I'm just writing this out. We are just, what we are doing, we are just projecting our vector v onto w, our vector v onto w. Okay, we are just projecting vector v onto w at a right angle. If you want to make me this kind of vector inner product using an animation, so-called a MANEM library, using a MANEM library, or just like a Grant Sanderson, we should have commented out, I will be generally making that video that you will be getting about the how we can visualize this at what happens in the vector inner product. Again, I'm recapitulating. The vector v, this is my vector v, and this is my vector w. This is my vector w, and our vector v is projecting on a w at a 90 degree, and this whole is the p, which is a projection of v. Okay, and this is whole called the concept of orthogonality. Okay, nothing to learn about the names, but the concept is orthogonality. What we are doing, we are just projecting v at a right angle by making a right triangle, you might be seeing here, and at a 90 degree, and the projection is the projection of vector v onto w. And we can write this as a p. Let's name a variable. Okay, now I think that we are very close to our solution. Now we have taken out the projection of v. We are taken out the projection of v. Now, if we have taken out the projection of a v, so what if w transpose v? W transpose v. Then this would be our projection times the norm of w. Times the norm of w, and this whole equation will give you the inner product of the two vectors w and v, and the inner product is w transpose v. And if w transpose v equals to p, which is a projection times the norm of w, and we take out the norm of w1 squared plus w2 squared. Okay, and just I'm going to recapitulate again. We are projecting v onto w at a 90 degree, and this whole is called p, which is a projection of a v onto w. Okay, and here is the solution, and now you can calculate the projection times the norm of a vector. Now we can get the answer. And another solution, and the simplest solution is but we are not going to use that, the thing of w. If we transpose w, it is in this, it will something like in a horizontal direction. So w1 and w2 multiplied this v1 and v2, we're going to get v1 plus w2 and v2. And we have just got this again. You might just do this and you will get the same answer here. It is very easy, but I would like to make you familiar with the concept of orthogonality. Okay, now you might be thinking, hey Ayush, can the projection be negative? Here the projection is greater than 0. It is greater than 0, and here it is positive. Here it is positive, and you might be thinking, can our projection can be negative? Yeah, absolutely it can be negative. So let me draw a line here. Yeah, this is the vector W, and let's say this is the vector V. This is vector V, and see here, and simply see that the angle between them are greater than 90 degree, So we have to take the projection at a 90 degree and opposite direction. So this hole that I've just darkened out is the projection. Just I've done is a 90 degree, this hole is the projection. And how do we plot the vector? This is also the key concept. First, this is a two-dimensional array, so we usually write W1 at the x-axis and the W2 at the y-axis. So this is my W1 and this is my W2, and again this is my V1 and again this is my V2. Again you can do the same, W1 and W2. Again for that the same. Okay, the projection can be the negative or the smaller than 0. Okay, and this all might be clear to you, and I think you might be familiar with the concept of orthogonality. Now let's talk about this is the part of the linear algebra. Now let's take a look at the large margin classifiers, and after this we will be recapitulating all those things, and we'll be taking a look at how actually large margin works. Sorry, how formed. Okay, so here I'm just making familiar that we can write in large margin this as a 1 by 2. This is the same, and theta 1 squared plus theta 2 squared. And you might be thinking, hey Ayush, how do you might feel very confident while writing only 2 thetas? Because it can be a number of thetas. But here what I have written here, we usually take theta for simplification, not usually. For simplification, we take theta 0 equals to 0, and the number of features is theta 1 and theta 2, which is a 2. Okay, so that's why I'm pretty confident to write this without saying to you. Okay, this is the reason behind it, is the number of features equals to 2. For simplification, I just written out. Okay, so this is the thing that I'm going to talk about. Now I can write this as 1 by 2 theta 1 squared plus theta 2 squared, just something like that, squared. Okay, I can write this something like that. And I can write this also as the norm of theta, means the length of the theta. It is the Pythagoras theorem. So I can write 1 by 2 times the norm of theta squared, because there is squared always left. Okay, at last we are going to get this equation. Okay, we have just optimizes this for the number of feature equals to 2 without taking the number of thetas examples. Okay, so now let's take a look at the real world example. Not a real world, this is, let's say this is the theta vector. This is my vector theta, and here we have a theta 1 because it's a two-dimensional vector theta 1, and this is my theta 2, and this is my theta. Okay, and we have taken our, let's say this is my data point. This is my data point. Okay, now if I project this data point onto the vector theta at a 90 degree, then this hole is P, and here P is the projection of the data point x1 onto the theta. It is the P here is the projection of x1 onto the theta. Okay, onto the vector theta. And just the same thing, and here we are taking the inner product, and the inner product is the P times the norm of theta, which is the vector, which is the actually vector onto the that kind of projection has been projected. Okay, so P times it is the theta transpose x, which is the P times the norm of theta, and that's why we take P as a projection times the norm of theta. So that's why I had make you familiar with the orthogonality concept. Again, I'm recapitulating. We are projecting our data point x1 onto the vector theta at a right angle, and these all are the projection of x onto the theta. And you might be thinking this is the pretty similar to W transpose V, what we have seen earlier. Okay, and I think this will be very clear to all of you seeing this video. Okay, now let's take a look at so many data points and how actually this large margin classifier had formed and what is the meaning behind that. Now, just see here is that we have, again, let's write 1/2 the norm of a theta squared. Okay, we can write this as for optimizing. So here we want just the previous thing, that is a projection times the norm of theta. Again, just showing you for simplification, I would like to take the number of features equals to 2 and our favorite theta 0 equals to 0 for simplification. Okay, and we usually take the norm of a theta by taking the square root theta 1 squared plus theta 2 squared. Okay, and by this you can take out the length of a theta. Okay, now let's draw a decision boundary that separates the positive and the negative examples. So this is my decision or a support vector machine decision boundary. This is my decision boundary, and let's denote this is a vector. And if I project this data point, let's denote this data point as x1 onto this vector at a 90 degree, then this is the small one here is the P, which is a projection of x1 onto the vector. Let's denote it as a W. Okay, now if I write P times let's denote P1 because we are going to take a lot of P's. P1 times the norm of a theta, norm of a W. Let's say W. Okay, P times the norm. Let's denote this not W. Let's denote as theta. P times the norm of a theta, and this would be not smaller than or equals to -1. Okay, if our y equals to, this would be the smaller than or equals to -1. Yeah, no, because it is very small. You can see here it is very small, and we want it to be very, very, very small so that our support vector machine always get a good predictions. So we want this Pi times the norm of a theta would be greater than, so we want this vector, the theta, so we want the norm of a theta very large so that this would be the more increase and we are going to get a good thing. but here it's a very small projection and this doesn't feels to be good. But if our norm of theta, this norm of theta would be large, then this happened to be a very good thing. Okay, now let's take another example. Now let's denote this data point onto the vector this at a right angle, and this small point. This small point is the projection. Let's note as a P2, and we want P2 times the norm of theta would be the greater than or equals to 1, and here it should be smaller than or equals to 1. It should be the smaller than or equals to 1, minus 1. Okay, and here we want the norm of theta to be very large, and here we want that that you might be seeing here, that is not very much good thing. That is not, it is very small projection. It is very small projection, but we want more, but we want a very high projection, so that this constraint should be clear. So for that we want the norm of theta to be large, so that this constraint follows the rule of that. Okay, so in the both condition, for the both condition, this one and this one, the norm of theta would be large, should be large. Okay, now let's take another look of example where we have a good thing here. So first of all, let me erase this. So the norm of theta would be large, so that this can get now here, let's say I would like to take this as a green. Now let's say we have a decision boundary. Which is this. Sorry. This is my decision boundary. Let's say this is my decision boundary. Yeah, this is my decision boundary. Okay, and here you might be seeing here that if I draw another line and another line, the margin between them, this is very, very large, and the support vector machine always wants to maximize this margin, and here the projection would be also good or a very large, and here the norm of theta is large, and so that's why both the constraints follow the rules and they are good to go, and we are good to have this kind of the support vector machine, large margin classifier, which separates out at maximum distances of the negative and the positive examples, and support vector machine always want to maximize this margin, and this is called the large margin classifiers. And we usually denote support vector machine as a large margin classifier, as it always wants, the support vector machine always wants to maximize their margin, so that's why they called a large margin classifier, and they just separates out the positive and the negative examples, and thus it gives us accurate predictions. So, and the hypothesis we have plotted, and this is also known as the hypothesis. We have plotted. So according to here, this is not very good thing. This is the thing that we want, those who follows two constraints, and here the norm of theta is large, and if you want to decrease the norm of theta, you can decrease and take a look at that. You will see there. Okay, now for the simplification, we have taken theta 0 equals to 0, and why we have taken. So let's say we have not taken the theta. So first of all, yeah, we have not taken the theta not equals to 0. So this is my xy plane. If not taken theta equals to 0, our decision boundary would be the large margin classifier would be something like without passing through the origin. So that's why we have set it the theta 0 equals to 0, so that it can pass through the origin for our simplification, and if we do not set, this will not pass through the origin. Okay, so that was the difference. So that's why I had taken a look at why we taken theta 0 equals to 0. And in the same way, you can take a look at the m number of examples just to show here is that 1 by 2. You can take a look at theta 1 squared plus theta 2 squared all the way down to theta m squared. Okay, and the norm of theta. So this is the margin. This is also called the large margin classifiers. Here it doesn't satisfy the constant of these twos, but here the projection is very large and the norm is very large, so norm of a theta should make it small and just see there. Okay, so I think that's give you enough intuition behind the support vector machine, and this might feel very interesting to you about the orthogonality concept. We are learning the new things, and this would be full of at that time you'll be full of confidence whenever you ask about the support vector machine, and you'll be definitely answering that. So I think that's it for this video, and I hope that you got some kind of knowledge. And in the next video, what I'm going to do is that I will bring you the video of kernels. Okay, the 2 or 3 videos will be coming for kernels, and these are also this important concepts. So that's it for this video, and before saying thank you to you, if you're new to the channel, be sure to subscribe this YouTube channel, press the notification button, and also press the subscribe button so that I can get motivated and bring up new contents. So that's it for this video, and I hope that you'll be carrying out in the next video. Thank you for seeing this video. I'll be catching up in the next video. Till then, bye bye.